Hello and welcome back. In this part of the lecture, I'm going to demonstrate how to use Excel Solver to provide a solution to the aggregate planning model. And of course, it's an optimal solution because Excel Solver has built-in algorithm that can deal with linear models such as the model that we are discussing for the aggregate planning problem here. So before demonstrating how Microsoft Excel Solver can be used, I would like to remind you about the decision variables that we have in the aggregate planning model. Now these are the decision variables, okay, which represent the variables that we would like to find values for such that the total costs are minimized. And of course, these are the different elements of the costs. So before using Excel Solver, Excel Solver actually deals with a kind of problems, mathematical problems that are called optimization problems. And in these optimization problems, before using Excel Solver, we need to have a mathematical formulation of the relationships of the decision variables to be used or to be entered into Excel Solver, and Excel Solver will try to find a solution. There are specific type of the optimization problems which is called linear programming models in which the relationships between the decision variables are expressed using linear equations and or inequalities, and as well as the objective function is expressed as a linear function of the decision variables. So the shape of the model that corresponds to the aggregate planning problem looks like the what is being represented here in this slide. In this mathematical formulation of the optimization problem of the aggregate planning model, you can see that we have an objective function that tries to minimize the total cost associated with the decisions. So this is what we call the objective function. Okay, this is how we formulate optimization problems. First, we need to define something called the objective function. Well, the objective function in our model is to minimize the total cost, which is represented mathematically using this formula. Now, when you look at this formula, you can see that all the costs that are involved in our model in the formulation of the objective function are simple relationships. We have the cost of inventory holding times the amount of the cost of hiring new worker times the number of workers hired in period T. Okay, then we have the cost of firing a worker times the number of fired workers, the cost of holding inventory times the quantity kept in inventory at the end of the period, the cost of regular production times the decision variable that represents the production quantity in period T, and so on. Now, all these elements or all these terms are summed up, and of course, we have a sigma notation here, which means we are summing up the values for all the periods that we have from T equals 1 to T capital. So this is called the objective function of our formulation of the aggregate planning model. After that, we have constraints. The constraints represent the mathematical relationships between the decision variables and the problem parameters. Remember, we have in the aggregate planning model these three equations, okay, which represent what the mathematical relationships that we talked about earlier. In addition to that, we have also non-negativity constraints or non-negativity relationships, which means all decision variables have to be non-negative. Now, this shape is called the mathematical formulation of the optimization model of the aggregate planning problem. Now, as you noticed, the three sets of constraints that we have here are also linear relationships. By linear relationships, we mean that all the variables appear in the form of a constant multiplied by the decision variable. We do not have something like the squared value of a decision variable or the multiplication of two decision variables. We do not have this shape. So this kind of relations or this kind of models in optimization are referred to as linear programming models. Luckily, linear programming models can be solved optimally, which means we can find values for the decision variables that give us the minimum total cost by using a method that's called the simplex method. The simplex method is very common, and it has been developed in 1940s. So and it's been there. It's very efficient for solving linear programming models of different sizes and types. The simplex method is implemented on Excel using which is called actually Excel Solver, or within the Excel Solver add-on. Excel Solver is an add-on that's like an additional software added to the Excel software. And this add-on software can solve or can provide optimal solutions for small-sized small-sized linear programming models using the simplex method. So let us see how Excel Solver can be used to solve the example that I have demonstrated in the first part of the lecture. So now we are going to go to Excel, Microsoft Excel, and I have here an extra sheet in which I have entered all the problem data as we have done before. Okay, and in addition to that, I have a table. Now this table is an empty table in which I have listed all the decision variables, okay, that we wish to have values for. Okay, and of course I have information for the demand. In addition to that, I have formulas for calculating the different cost elements, okay, which actually is based on the values given in the table, as you can see here. Okay, and then of course we have the total cost calculated in this cell, which is the summation of the different cost elements. Now, what I'm going to do is I'm going to use Excel Solver add-on to solve this linear programming model for this example. Now, first let us see how to install Excel Solver add-on if it is not available on your current installation. First, you need to go to the File tab. Here you have in the menu something called, in the bottom, something called Options. And then you have in the side tab here something called Add-ins. And at the end of the form you have a button which says Go. Of course, the default is Excel add-ins. So you click on Go. And then you have a list of the add-ins that actually you can add to your current installation of Microsoft Excel. One of them is Solver add-in. It's not checked here, as you can see, so I will check it. Okay, and then click OK. Now it installs the Excel Solver add-in to your current installation of Excel. Now you can find Excel Solver here in the Data tab. You can see here a button is added which says Solver. Okay, Solver is, as mentioned here, is what if analysis tool that can find optimum value for and so and so. So now let us see how to use this tool. Okay, in order to start solving your model, we need exactly to enter the mathematical relationships that define the objective function and the constraints. Now I have already defined how the objective function is calculated in this cell, right? Because it's the summation of the values of these cells, and these values are already calculated based on the decision variables that will be assigned to these cells. So it's already calculated, the total cost is already calculated here. Okay, so in order to start solving our model, what I'm going to do is I'm going to click on this cell, which represents the objective function value, okay, the calculated objective function value, and then I will click on the solver button here. It directly opens a dialog box. In that dialog box, okay, the first part here says set objective. In this cell, okay, I'm going to click on this button and then click on this cell, okay, and click on this button again. Now, this means what? This means I entered the definition of the objective function based on the calculations that we have done, which appears in the cell labeled G43. Okay. Next, we choose what is the direction of our model. Is it maximization? Do we need to maximize the value of the objective function? Or minimization, we wish to minimize the value, or you wish to find a specific value for the objective function. Of course, in our case, we would like to minimize, because the objective function is to minimize the value of the objective function, which is the total cost. Next, in this cell, we need to define the decision variables that we wish to consider in our model. Now, the decision variables, now I'll click on this button to allow me to enter, okay, freely on the Excel sheet. And then I will go to our table, because the decision variables are defined based on the cells provided in our table. The decision variables include what? Include these cells, which represent the number of workers in a given period. Now I will press Ctrl button and hold it to highlight the other cells that we wish to consider as decision variables. Here also the number of hired workers in a period, number of fired workers, they are all defined as decision variables in our model. What else? Yeah, the production quantity is also decision variable. The overtime, okay, are also decision variables. The undertime are also included as decision variables. The inventory, the backlogged quantity, the subcontracted quantities. All these cells represent the decision variables that we have in our problem. Now I'm going to click on this again and to go back to our dialog box. Next, I'm going to add the constraints of our model one by one. Let's go back to the slides and see how the constraints look like. Here it is. Now, we have a constraint. The first constraint here says, well, Wt equals Wt minus 1 plus Ht minus Ft. So that's exactly the equation that represents the number of workers, how the number of workers changes over time. And we have to repeat that for all the 12 periods that we have in our example. So let us see how to do that. We'll go back to our Excel solver. Okay. We are going to add 12 constraints for each Wt, Ht, Ft to represent their relationships. So I'm going to click, all the constraints will appear in that box here. I'm going to add the first constraint, and let us recall here. It says the first constraint, the number of workers in a given period equals, so I will choose here the equal sign, equals the number of workers in a previous period plus the number of workers hired in the current period minus the number of workers fired in that period. Okay, this will give us the balance for the number of workers equation. Okay, and then I will click add, and then I will have to repeat this again for all other periods. So I'm going to add here W2, and it should equal, okay, the number of workers in the previous period plus the number of workers to be hired minus the number of workers that will be fired. Okay, and then I will repeat that for all other constraints. So I will do it offline. Okay, but here in the video I'm just showing you two examples of how to enter these equations. I have to repeat that 12 times. Okay, now when I do that, as you can see here, the two constraints are already added to our model. So this is the first set of constraints that we have in our model, which represents the balance for the number of workers. Now we have another relationship which says, well, the amount of production equals the capacity minus the undertime. And remember, in our example, we do not have overtime here. The overtime should be 0. Okay, so I mean, you can actually neglect the overtime in our example, or you can add it here. Or actually the overtime production is already added here in the inventory balance equation. All right. So let us enter this relationship here, which says the production quantity in a period T equals K times N times W in that period minus U sub T. So I'll go back to my Excel file, okay, and add these constraints. So let us add one more constraint here. Okay, so the production quantity in a given period, that's going to be here, is exactly equal to the value of K times N times WT minus the amount of underproduction in that period. So that's the first equation. Again, I will do another period for you, and then I will do the rest offline. So we have the production for period 2 equals the available capacity minus the under time production. Okay, now this will appear here. As you can see here, these are the two constraints added. Okay, so again, we are going to repeat that for the 12 periods that we have. So this is going to be repeated 12 times. Next, we will have the inventory balance equation, okay, which relates the inventory with the backlogged quantity, okay, and then the total production plus the overtime plus subcontracted quantity minus the demand. So we will add another constraint here, and in that constraint we are going to say or define it as follows. Well, this constraint says, well, the inventory at the end of the first period minus the backlogged quantity at the end of the first period is equal to the inventory in the previous period minus the backlogged quantity in the previous period plus, I will open a bracket here. It says, well, P sub T, okay, the production quantity that you wish to have, plus the overtime quantity, plus the subcontracted quantity, minus the demand in that period. Okay, and I will close the bracket. let me add one more for that. Now it says cell reference box is empty or content is not valid. Okay, so it's something went wrong. So basically, actually, I need to have here in this cell. It's like you should have actually okay, one variable only. So to avoid this mistake, so what I'm going to do, I'm going to put only the production in the first period. Okay, and then I would put the backlogged quantity in the other side of the equation. Okay, and this will be okay. So it's yeah, let me do it again here. Let me delete that and repeat that again. So now in this constraint, we will add, okay, we will put the production quantity on one side, the left-hand side, okay, sorry, the inventory on one side, and then we will add the backlogged quantity, okay, add the inventory, subtract the backlogged quantity in the previous period, and then add open brackets, and then we will have here the production quantity plus the overtime production plus the subcontracted production minus the demand. Close the bracket and it should work now. Okay, so this is how to add this constraint. Now we are going to repeat that again for the rest of the periods. This will constitute 12 periods. Okay. Now I will do that offline, and then I will give you the final dialog box in which all the constraints are included. Now I have entered all the required constraints of the model, as you can see here. Okay. And in addition to these constraints, I have added also, I will show you how to add another two constraints. The sets of constraints that we have already added here are actually the three sets of constraints that we have in the linear programming model as we have demonstrated earlier. Now, for the specific problem that we are studying here, okay, we have a restriction that the number of backlogged quantities should be zero. You cannot have any shortage or backlogged quantity in your solution. So in this case, okay, I'm going to add a constraint to the model that takes into consideration that the backlogged quantities should always be zero. Okay, and of course the backlogged quantities are listed here in this column, in column K. So what I'm going to do is I'm going to add another constraint to the model, and in that constraint I'm going to define that the values, all the values that we have in these cells should always be equal to zero. In addition to this constraint, we have another constraint that says you cannot have also overtime, and that's specific to this example. So I'm going again to highlight these cells which represent the OT variables and define them as zeros. Okay, that's all what you need to do. Now, our model contains all sets of constraints, in addition to the constraints related to the backlogging and the overtime. Now, we have here a check mark that says make unconstrained variables non-negative. So the non-negativity constraints are inherently defined by just making these checkbox checked. And then we are going to select the solver. The solution method is the simplex linear programming because all the constraints that we have are linear and the objective function is linear, so it's sufficient to solve this model using the clicks LP, which will give you the optimal solution. Now we have everything is settled. Now let us run the solver and see what we will get. Solve. It says optimal cell. Oh yeah, probably the optimal cell has changed. While yeah, this is the optimal cell. Okay, so this should be okay. Now solve. It gives you a dialog box that says, well, would you like to keep the current optimal solution that the solver has found, or you just restore the original values? Of course, we didn't have any original values, so I will click OK. And here is the result. Now, as you can see here, the total cost is actually less than the other costs that we had in the mixed or any other method. So in the mixed here, we have the total cost is 186,000 approximately, while the solver gave us 168,000 approximately. So now let us have a look on the solution. Well, when you look at the solution, you will see that, well, yeah, it seems like the optimal solution maintains a fixed WT value, okay? But we have a problem here, which is the number of workers given in the 10th month is 4.8. Now, this is not acceptable, of course, by any means. Okay, so it's like, yeah, we need to add some restrictions about the number of workers, maybe. All right, so let's go back to the solver. We would like actually to restrict the number of workers to be integer value. So we are going to add a constraint here that says all the values that we have here, okay, for this decision variable, okay, and then select here should be integer values and click OK. Now let us run solver again. Oh yeah, the solution is a little bit higher, okay, and as you can see here, the values for WT are all integer values. Sometimes the solution that you will get here might be sometimes close to zero. So what you need to do is just put zero here. It doesn't make a huge difference. But the point is sometimes, the Excel solver might have some rounding of error. That's why you see these kind of answers or solutions. Now, as you can see here, the optimal solution actually uses the full capacity, okay, and stores inventory, okay, at the beginning in the first 4 months, and then it subcontracts for the remaining months. In the last month, actually, also we have inventory of 3 aggregate units at the end of the last month, okay. And of course, probably the cost of keeping inventory in the last period is not that big, right? Compared to might be hiring or firing a worker or something like that. So, I mean, this is the optimal solution that we can get. So this is, a demonstration of how to use Excel solver to solve this linear programming model. It's very easy to use. Once you have modeled your problem correctly, then you can actually obtain your optimal solution. The only restriction that we have on Excel solver is that if your problem is really big, Excel solver will not be able to solve it for you. It's like they have put some problem size restrictions in this add-in. If you wish, of course, to solve larger problems that cannot be solved by Excel solver, probably you can add another software, purchase it, and add it to Microsoft Excel, and it can do the same thing for you. Well, that's it for today. Thank you for your listening, and see you inshallah next week, and have a nice day.